Newton. Why is he a part of the story here? Well, we've just finished Kepler. We have Kepler's laws that describe the motions of the planets, and it describes them perfectly. So why is there need to do anything else? And Kepler and many others probably thought there's no need to do anything else. But what Newton introduces is the concept of physical law. And the planets are traveling in these elliptical orbits. Why are they traveling in these elliptical orbits? Is there an underlying principle? Or is that the principle? That, according to Kepler, the principle is his first law. They travel on elliptical orbits. His second law, his third law. But Newton said there are more fundamental underlying principles that govern not just the motions of the planets, but the motions of everything. And if we can describe Newton's laws, which are these underlying physical principles governing motion, you could then describe the motions of everything, including the motions of the planets. So he's trying to come up with a broader understanding of motion in general. So we should just point out the difference here. Different types of laws. Empirical law is what Kepler did. He's just describing it mathematically. He's not explaining it from some underlying set of physical principles. What Newton's introducing is physical law. And if he does it right, which of course he will, and he does, then we'll come up with the exact same description. We won't have a better description of the motion of the planets, but we'll have a better understanding of why that motion is the way it is. So, Newton was a thinker. He sat around and thought about a great many things. But what really brought this to the forefront, strangely, was the bubonic plague. So we can thank the bubonic plague for the birth of modern physics. And that's because it came through Cambridge, and Newton was a professor at Cambridge, teaching lectures similar to this one. And this was 1665, the bubonic plague came by, and he didn't want to catch it, understandably, so he decided to retire to the countryside. He's from a family of some means, and they had a countryside estate, and so he decided to wait it out there. He didn't have much to do except sit around and think about things. He wasn't burdened by teaching. And so he sat around and thought about physical law and laws of motion, and came up to some rather important insights and summarized it in this book here, the Principia, which you should just call the Principia. But its full title is Philosophy Naturalis Principia Mathematica. And forgive me if my Latin pronunciation's bad. I don't speak Latin. But I do know enough that the way it works is all the descriptors are reversed. So if you want to translate this, you go from the end back to the beginning. It's mathematical principles of natural philosophy. So what's natural philosophy? Well, that's science, essentially physics, chemistry, kind of your harder sciences, or more broadly interpreted, just science. It wasn't called physics back then. Physics hadn't been invented. It's just called the philosophy of the natural world. There are all sorts of different types of philosophies. In fact, I'm a PhD. I'm a doctor of philosophy. And that sounds kind of strange because in the modern day, we think of philosophy meaning a particular type of line of thought. If you ask me to name famous philosophers, I could probably come up with a handful and maybe even tell you what they were thinking about, but not much more. But back then, there are all sorts of different types of philosophy. And natural philosophy is what evolved into kind of the quote, hard sciences. So mathematical principles of physics is basically what this is. So 3 laws, N1, 2, and 3, just like Kepler gave us 3 laws, Newton gives us 3 laws. Here's Newton's first law. I'll read it here. Every body continues in a state of rest or a state of uniform motion in a straight line, either one state or the other, unless it is compelled to change that state by a force acting on it. So I'll give you a chance to write that down. But we've got 3 parts here. You got at rest, state of uniform motion, that's constant speed, constant velocity. And 3, we have to talk about forces. So he's saying if something's at rest, it will stay at rest. If something's moving at constant speed in a particular direction, it will stay moving at constant speed in that direction. Unless Either of those states can be disturbed by a force acting upon it. As soon as the force is done acting, it goes back to one of these two natural states. So here we go. So here's a ball sitting on a table. We'll consider all these three cases. The first case, it's just sitting there at rest. So this seems, if you look at Newton's law, at first you think, boy, this is really intuitive. It's so intuitive, why would we even describe it as a law? But parts of this are actually kind of insightful. The first part's very intuitive, though. If you have something at rest, it stays at rest. Like I have a ball right here. The ball is sitting here on the table. It's at rest. It will stay at rest unless it is compelled to change that state by a force acting on it. So if I go and push it, it will no longer be at rest. Pretty intuitive. The second one is a little bit more insightful. If the ball is moving at a constant speed, Newton says it will continue to move in that direction at that speed forever and ever and ever unless compelled to change that state by a force acting on it. And this is kind of insightful because suppose I'm not going to do it here because I'll mess it up, but imagine I have a really long table and I roll this ball. Is it going to continue going at a constant speed forever and ever? What's it going to do? It's going to stop. And why is it going to stop? Friction. And friction is a force. Yeah. Back then they thought there was one natural state. The natural state of something is to be at rest. If I put something in motion, it eventually stops and goes back to the natural state. Newton was insightful enough to know that that's not true. Things moving at constant speed is the natural state. Constant speed of 0 is at rest. So cases A and cases B are the same thing. Moving at a constant speed. No accelerations, no decelerations. That's the natural state. He said you can change the natural state by a force acting upon it. And we just said friction is an example of a force. Acts upon the ball, slows it down, and stops it. You can think about this by thinking about a scenario with less friction. Consider an air hockey table, a really long, big air hockey table. I have the puck and I send it on its way. It will go for a very, very, very long time before it slows down. Much farther than rolling the ball would. Now, it'll eventually slow down because there are frictional forces there as well. It has to go through the atmosphere, and it's, the air molecules are bumping up against it, slowing it down. And so that's a source of friction as well. But you can go to an even more frictionless environment. You can go to space. If I'm out there in space, away from all forces, gravitational fields, everything, and I take an object, I throw it. As soon as I let go, it's traveling in a particular direction, particular speed, and I think you can all imagine it would just keep going forever and ever in that direction with that speed. Right? That makes sense in space? Now, in reality, space is not empty. There are little gas particles. Eventually, it'll bump into enough of those that it might stop as well. It's hard to come up with a purely frictionless environment, but Newton was insightful enough to intuit how things would behave in that scenario. And then we have case 3, changing these states, a force acting upon them. Someone give me a simple definition for a force. A what or a what? Push or a pull. That's a very clean way to define force. We don't have to get too technical. The forces are pushes or pulls. And we can define two classes of forces here. We can have instantaneous, and we can have continuous. Now, instantaneous, I'm going to put in quotes. There's really no such thing as an instant force. All forces will be applied over a particular period of time, not over just one instant of time, but it can be a very short period of time. And what you see here is about as close to that as you're going to get. The ball's rolling along, not disturbed by any forces, so it's moving in a straight line, uniform speed. Then the green arrow indicates a force has been applied to it. Maybe another ball hit it. Like if you're playing pool, you hit one ball with another. There is a brief window of time where the two balls are in contact, and that's when the force is being applied. When the balls are out of contact again, no force is being applied, but its trajectory has been changed, its speed might have been changed. As soon as the force ends, it's back to uniform motion in a straight line, maybe just a different straight line. But I put instantaneous in quotes because even if you hit one full ball against another,
there is a window in time in which they're in contact. You can't see it, but again, the balls are made of molecules. They come together, and the molecules will compress a little bit and then rebound, and the ball will go off in a different direction. So it's not an instant in time. There's actually a window there, a beginning and an end when the force is being applied. But it's close to instant as you can get. What are some examples of continuous forces? We've already mentioned one. Friction. And gravity is another example of a continuous force. It's always at work. It doesn't turn on and off. And gravity is ultimately the reason we're going through Newton's laws. We're going to show, the idea here is we're going to show, once we get through the three laws, you could use them to derive Kepler's laws. Kepler's are merely empirical, but Newton finds a physical basis for them, and the physical basis is these three laws. Okay, that's N1. N2 is Newton's second law. And what it does is it relates a force to the acceleration you feel when you're experiencing that force. So when a force, let's call that quantity F, acts on a body of mass, and we'll say the mass is m, it produces in it an acceleration, a, equal to the force divided by the mass. And this is something you can figure out just playing around in the laboratory. Maybe you have a little motor like this one here. We'll play with it in a second, but I turn it on, and it will, it's a fan car, so it pulls the wind. So it's a constant, oh, it goes this way. It's generating a force constantly by moving the wind through it using the energy in the battery. So it generates in it, here I'll clear a path, an acceleration. We'll just see this. So it's going faster and faster and faster. Don't worry, I brought that for more than just that. We'll play with this in a second. Acceleration is force divided by mass. So I'm sure he conducted a few simple experiments, measured a few things, and figured out that this is the relationship between these quantities. Or maybe he just did it all in his head, and Newton was capable of that. Acceleration is force divided by mass. It was more commonly written as force equals mass times acceleration. F equals ma. You might have heard that before. Okay, before we do an example of how these things relate to one another, let's just write down a few quantities first. Let's go back to one we all know. Velocity is what? Velocity is defined as what over what? Yeah. Distance over time, or we can say change in distance over change in time. Delta means change. So if you're changing your distance over a particular period of time, like you're driving in a car at constant velocity, that's how you compute the velocity. And so the units are meters per second for velocity. Acceleration, how would we define that? Change in velocity over change in time. So there's a difference between driving in your car at constant velocity and accelerating from, say, 0 to 60, or decelerating from 60 to 0. So if you're changing your velocity at a uniform rate with time, you have an acceleration, delta v over t. And so the units here would be meters per second, or meters per second squared. Accelerations are measured in meters per second squared. And so the force, if we want to put units on the force is mass times acceleration. So the units are going to be kilograms, meters per second squared. Kilogram from the mass, meter per second squared from the acceleration. We also just call this a Newton. Because why not? Kilogram meter per second squared is a mouthful. We'll just give it a more appropriate name. Newton came up with this, so we'll name it after him. Okay, so let's play with the fan card just for a second, see how this all relates. I'm sorry if it's a little difficult to see. But the fan car has a particular mass. It generates a constant force. It's pushing that air through at a constant rate. It's generating a constant force. It has a particular mass, so together we get particular acceleration. We've done this once, I'll just do it again. It's going faster and faster and faster and faster. And I almost always drop it or get my finger stuck in it, so I'm hoping for the best here. Okay, I just put a 1 kilogram weight on the car. It should move slower.
the car is probably about 1 kilogram too, so now I've kind of doubled the mass. It should accelerate half as quickly, or half as fast. So, do you all agree this is a slower acceleration? Okay. And just to drive the point home, I'll put another kilogram on top of it. And so this should slow it down again. Okay, so it is accelerating, sort of, very slowly. I think frictional forces have overcome here, so this is not a friction-free experiment, so it kind of messed with our experiment here, but you get the idea. The acceleration was so low it could not overcome the force of friction. Or maybe the table is tipped. That was a very different example of using the force. Okay. Where was I? Let's see. Okay, Newton's third law. Here's one you've heard before, I'm certain, though probably not in this context, and this is the original context. To every action, there's an equal and opposite reaction. Ever hear someone say that before? Usually it's done as a threat, like, you screw me, I'm going to screw you. But this is the original connotation for that. Instead of action and reaction, think force. They mean the same thing. For every force, there's an equal and opposite force. You can't generate a force out of nothing. That's another way of saying this. There's no such thing as a free force. Sounds like there's no such thing as a free lunch, a phrase you get in economics. Maybe they have a common origin as well. Anyway, you can't generate a force out of nothing. If you're going to give something a force, there has to be an equal and opposite force felt somewhere. They must balance out. So I got 2 examples of this here.
Okay, so some examples. So, there it is, my first car. I know, not spectacular, but I loved it. In 1994 Ford Tempo. I call it the 94 FT for short, because it sounds cooler than it really was. So, in my example, I'm driving along in the freeway. I couldn't take a picture of myself while driving, so you just have to imagine that I'm driving along on the freeway. And then up behind me comes an 18-wheeler. Oh, that doesn't look good. And so it's coming up behind me, and we have a little accident here. Application of Newton's third law. By Newton's third law, it says every force, there's an equal and opposite force. Given that, I shouldn't have said that because I kind of gave the answer away. Who's feeling the greater force here, me or the 18-wheeler? I gave you the hint and you all got it wrong. It's the same force. Okay, you're thinking, what? I must be feeling greater force. No, by Newton's third law, same force. There's a force being applied to me by the 18-wheeler, and there's also a force that I'm applying back onto the 18-wheeler. And those 2 forces are equal and opposite. You can't generate a force out of nowhere. What differs is the acceleration. So go back to Newton's second law. Let's look at it in this form right here. Same force, but who has the lower mass? I do, in the Ford Tempo. And so the Ford Tempo is lower mass. That same force divided by the low mass is a large acceleration. If I take that same force and divide by the mass of the 18-wheeler, big mass, small acceleration. So the difference in what we're feeling there is the acceleration. I'm going to have significant whiplash because of that significant acceleration. The 18-wheeler might not even know it hit anything and just keep on going because its acceleration in the opposite direction, which we call a deceleration, would be small by the ratio of the masses. That's one example. Here's another. Let's see, I have a little video here. A cannon being fired. It also shows that you can't have a free force. Cannon. So, when the charge blows, it's going to push the cannonball out with a big force. The cannonball goes in the forward direction, but you can't have a force generated out of nowhere, so the cannon is going to actually roll backwards. The cannon's more massive, so its acceleration in the backwards direction is less. The cannonball is less massive, its acceleration in the forward direction is more, but those two forces, the force of the cannonball moving forward, the force of the cannon moving backwards, are the same. Everything make sense so far? Newton's 1, 2, 3? Okay.